Alrighty, folks. Today we're going to be talking about section 3.5, which, as I mentioned last time, is all about higher derivatives. And really, this is mostly talking about notation, right? So, the higher derivatives, this that we've been talking about, is the first derivative, right? This is the notation for the second derivative, and all it means is that you take the first derivative function, whatever it is, and then you take the derivative of it again. Right, and then we can keep going, right? You can put 3 primes up there. You can cube all of the relative pieces, and that just means taking the second derivative and taking the derivative of that, and you get the third derivative. And I'm going to do one more just because there's a slight notation change, right? 3 is the limit of the number of primes that we put up there. So if we want to indicate the fourth derivative, we do it like a power, but we put it in parentheses specifically so we don't confuse it with the fourth power, right? When I say this, when I write this down, I do not mean 4 to the fourth. That is not, or f to the fourth, that's not the fourth power of f. That is the fourth derivative of x. Right, so that's just, this is the third derivative of f, and then you take the derivative, and that's the fourth derivative. Right, but it's very important to put those parentheses there, because otherwise it would be impossible to tell the difference between the fourth derivative and the fourth power of f. Right, and so if we want the derivative specifically, then we put parentheses around that number there. Right, so one other sort of vocabulary thing is that if we're back to the idea that s of t is a position function, right, then v of t, which is the derivative of s, is velocity, and a of t, which is the derivative of velocity, which means that it's the second derivative of position, is acceleration. And there's actually more. If you take the third derivative of position, you get something that's named, and I've forgotten what it was, and it's never in any calculus textbooks because we don't care about it. It's a physics thing. The fourth derivative has a name. The fifth derivative has a name. Those are the only ones that I'm sure about, but the sixth might have a name. But all it is just they it's something they wanted to use enough, and it had its own particular meaning that they wanted to give it a name. Right. So we'll do some problems. So let's find, we'll do a couple real quick ones. Let's find the third derivative, and the fifth derivative of f of x equals 3x to the fourth plus 10x squared. Let's make that cubed. Minus 3x squared plus 2x minus 7. All right? So if you want to find a higher derivative, there's nothing for it to do except find all the derivatives on the way. So first we need to find f prime of x. That's going to be a bunch of power rule usage, so we're going to bring the power down front and then make it one less. We're going to bring the power around front and make it one less. We're going to bring the power around front, make it one less. Linear means the x's just disappear and constants go away. Right? So one thing that we might notice, and as we think about things and go through this, is take note about how the powers are behaving as we keep taking derivatives. So we take the second derivative, we bring the power down front and make it one less. We bring the power down front and make it one less. It's linear, so the x goes away, and then the constant just goes away altogether. Right? And then lastly, the third derivative, we bring the power down front and make the power go down by 1. This is linear, so we just get the coefficient, and the constant goes away. Right? So what we can notice is, so one thing, the leading term, I've completely lost the vocabulary word I was looking for there. But the highest power goes down by 1 each time. In fact, all of the powers go down by 1 each time. Right? So we can sort of expect to have the power on the third derivative be 3 less than what we started, and that's exactly what happens, right? 1 is 3 less than 4. Also, one thing that we notice is that, right, these pieces sort of kept along the whole way, but these guys just disappeared, right? And in fact, there's a pattern to what stayed and what disappeared, right? The stuff that stayed had a power that was at least as big as the derivative that we wanted, and the stuff that disappeared had a power smaller than the derivative that we wanted, right? And we can see that if we keep going, if we want the fourth derivative, then, well, we've got this linear term, so 72, and now this has gone away. And then the fifth is just 0, right? So everything that has a power higher than the derivative we're taking stuck around. Everything that had a power lower disappeared. For this last one, everything had a power that was lower than 5, so the derivative itself is gone, right? So that lets us do impressive looking problems, like find the 20th derivative of f of x equals negative 5x to the 16th plus 11x to the 13th minus 22x to the 10th plus 3x to the 7th minus 19x squared plus 11, right? In this case, you don't have to do any work because this is a polynomial and all of its powers are less than the derivative that you're taking. So much like what happened with the fifth derivative of f here, it's just going to be 0. Right? So that's a nice pattern to keep a hold of. Right? It's not always going to be that useful, right? If we have something like find the second derivative of this function, right, we might notice that all the powers of x, right, are less than the derivative that we're taking, but this is not a polynomial, so we don't get to take our shortcut, right? This polynomial, or this shortcut that we're taking right here, works for polynomials, and not anything else, right? So for this one, we actually do have to put in the steps. So first we have to find the first derivative, right? That's going to take the product rule. So it's going to be the derivative of x times e to the x plus x times the derivative of e to the x. So that's 1 times e to the x plus x e to the x. So that's e to the x plus x e to the x. Now the second derivative is going to involve taking the derivative of this guy. So this is going to be e to the x plus x e to the x, taking the derivative. The sum rule says that we can break that down to its individual terms. And thankfully, the piece that would be annoying here, we've already done, right? The derivative of e to the x is just e to the x. That's easy and done, right? The derivative of x e to the x, well, we just got done finding that, right? So, we already figured out that the derivative of x e to the x was e to the x plus x e to the x. Right, so maybe we simplify it a little. And we're good to go there. Let's see. Yeah, that's about as fun a problem I can come up with until next section, where we'll get to add a couple of baseline functions that we can deal with, right? So far we know what to do for polynomials and e to the x. And we can add polynomials to each other and to e and the x. We can subtract them. We can multiply polynomials by each other and by e to the x. We can divide polynomials by each other and by e to the x. But that's all we can do, right? So there's a limited number of examples there. So next section, we're going to add the trigonometric functions to the list of things we know, so that we'll have a list of 6 new derivatives, and then after that we'll be able to come up with a whole bunch more, because we'll be able to multiply polynomials and e to the x by trig functions, divide, add, subtract, so we get a whole bunch more examples that we can work through once we have a more robust library of functions. So that'll be what we talk about next time.